Now, in this chapter, we are going to focus on mechanical energy. Okay, what is the total mechanical energy? Total mechanical energy is made up of two types of energies: kinetic energy and potential energy. That together makes total mechanical energy. Right? Now, what is the kinetic energy and what is potential energy? How do you derive them? What is the derivation? Let us see that. Alright? Fine. So, we know that work is equal to force into displacement. Correct? So, right now what are we doing? We are doing the derivation for kinetic energy. What are we doing now? Derivation for kinetic energy. Kinetic energy. Okay? Now, by definition, what is work? By definition, work is equal to force into displacement, F into S. We know F is equal to m into A, Newton's second law of motion, force equation. F is equal to m dot A, right? And what is S? And S is equal to ut plus half at square. Newton's second equation of motion, S is equal to ut plus half at square. Now, when you began the problem, what was the background? How did the body start? The body started from rest. So here you have a body of mass m which starts from rest, means u is equal to 0, and then gains uniform velocity. Okay, it increases its velocity uniformly and attains an acceleration of a. And by doing this, what was the time taken? T. So if I have to rewind and tell you this in a flow, then what will I say? I will say, consider a body of mass m with an initial velocity u, okay, having final velocity v in time t. Let the acceleration in this time t be a and the displacement of the body be s. Okay, the force F causes this displacement, therefore work is equal to F dot S. Here there was a force F acting on the body, so there was a body here. You can probably draw it and show. So here this is mass m, there is a force which is of F which is applied on it, and that force causes an acceleration a on this mass. Okay, initially the body was at rest, so u is equal to 0, and then when it starts moving, let's say it attains a final velocity of v here, and the time that it took to reach from this place to this place, supposing that time is t. Okay, so this is the situation we are dealing with here, and we want to find what will be the kinetic energy of this body. How much kinetic energy will it possess? So F is equal to m into A, S is equal to ut plus half at square, but the body started from rest, so u value is 0, and therefore we have S is equal to half at square. Right? So if I put this in my earlier equation, then I will have work done is equal to ma into half at square. This is what I will get. How did I get ma? From here. Force into S. What is force? ma. What is S? Half at square. So put ma, put half at square, you get w. Correct? So this I will call it as Roman number 1, this I will call it as Roman number 2, and then I can say from 1 and 2, w will be ma into half at square. So what will I get therefore? Therefore w is going to be half a square t square multiplied by m. Half a square t square multiplied by m. Now, we know from the Newton's first kinetic equation that V is equal to U plus AT. V is equal to U plus AT. So we will say now V is equal to U plus AT. Therefore, V is equal to 0 plus AT. Why 0? Because the body started from rest. So U value is 0. So V is equal to AT, right, in that case. So therefore, what will be V square? So V square is going to be A square T square. So V square will be A square T square. What did you do? Squaring both sides. You have squared both sides. So V square is equal to A square T square. Now, look at this. A square T square. So what is A square T square? V square. So I will put V square there. So I will say therefore W is equal to half into V square into M, and that gives me the final expression for kinetic energy. So W is equal to half mv square. This is the work done, and this work is done because of the motion, and it is stored. This work done is expressed by the body as its kinetic energy, right? Fine. This work is done due to the kinetic energy due to motion. Fine. And therefore we will say this work is done due to kinetic energy possessed by the body, due to its motion, right? Hence you can say W is equal to the kinetic energy. If W is kinetic energy, so this W is nothing but kinetic energy. So kinetic energy will also be half mv square. Hence proved. So this gives us the derivation of kinetic energy. So kinetic energy is equal to half mv square. So we will now prove the expression for, we will derive the expression for potential energy, right? Now, we all know that the work done by any body, okay, any body which is at, let's say, rest, what is the energy that I possess? It's going to be force into displacement. Yeah, fine. Supposing I am standing at a height h, then I will say it is mg into displacement. So W is equal to mg into height. So W is equal to mgh. Alright. Work done by, due to my position, is because of my weight. That's the force acting on the body. So right now the force acting is my weight, which is mg, multiplied by the displacement, that is s, and that displacement for potential energy is the difference between the surface and the height. So we call it h, and therefore the work done becomes mg into h. So that is the work done, and this work done appears as the potential energy of the body. So this work done is due to the position of the body. Hence W is equal to the potential energy. So potential energy will be equal to mgh. So relatively a shorter derivation as compared to kinetic energy. This is how it is. Okay, so we have derived the potential energy of a body. So 1 joule of energy is how much? Or 1 joule of work is how much? 1 joule of work is done when a force of 1 Newton displaces a body through 1 meter. Means you apply a force of 1 Newton on a body, and that body moves for 1 meter. The displacement is 1 meter. Then we say that the work done is 1 joule. 1 joule of work is done. Right? So 1 joule is equal to 1 Newton into 1 meter. This is the SI unit. We have to convert into CGS. In CGS, what will be work? 1 erg will be what? 1 dyne into 1 centimeter. Same way. Just like in SI system, 1 joule is 1 Newton into 1 meter. Why? Newton means SI unit, meter is SI unit, so work will also be SI unit. Now, if you consider the force in CGS, displacement also CGS, then the work that you will get will be CGS. That is erg, right? So, by definition, 1 joule is going to be 1 Newton into 1 meter, and 1 erg is going to be 1 dyne into 1 centimeter. This is by definition, right? Now, we will see the relation between the two. What is the relation between 1 joule and 1 erg? Now, let's see that. So, we know 1 joule is equal to 1 Newton into 1 meter. Okay? Therefore, 1 joule is equal to 1 Newton is how many dynes? 10 raised to 5 dynes. 10 raised to 5 dynes. 1 meter is how many centimeter? 10 raised to 2 centimeter. So therefore, 1 joule is equal to 10 raised to 5 into 10 raised to 2, 10 raised to 7 dyne centimeter. Correct? What is dyne centimeter? What is dyne centimeter? 1 erg. So therefore, 1 joule is equal to 10 raised to 7 erg. You will say, since 1 dyne centimeter is equal to 1 erg. Okay? Fine?